Hello everyone and welcome back to our discussion on processor management in operating systems. In our previous session, we explored some fundamentals of processor management, including scheduling algorithm, process states, and CPU allocation strategies. Now, today in part 2, we'll delve deeper into advanced concepts such as multiprocessing, multitasking, throughput, turnaround time, waiting time. These are some key factors that influence system performance and efficiency. So, by the end of this lecture, you should have a solid understanding of how modern operating systems handle processor scheduling and resource allocation to ensure smooth multitasking and efficient system performance. Now, let's take a look at two fundamental concepts, um, which is multitasking and multiprocessing. So, what is the difference or what does it mean? Multitasking refers to an operating system's ability um, to handle multiple processes seamlessly and simultaneously. This is achieved through rapid switching between tasks on a single CPU using time sharing. We categorize multitasking into two types. First is preemptive multitasking and second is cooperative multitasking. So first one is where the OS actively allocates time slots to processes, and the second one is where processes voluntarily yield control. So an everyday example of multitasking is like running a web browser, um, a text editor, and a music player on a single CPU. So this is an example of an everyday task. Now, on the other hand, multiprocessing involves using multiple CPUs to execute different processes concurrently. Each processor operates independently, increasing overall system efficiency. There are two main types. First is symmetric and then asymmetric. Symmetric, where all CPUs share the same operating system and memory, and asymmetric is where one CPU controls the system while others handle specific tasks. And a real world example of multiprocessing would be a server handling multiple client requests using multiple CPUs. Okay, now next let's discuss an important performance metric in computing, which is throughput. Now, throughput measures the amount of work or data processed by a system within a given time frame. It is crucial for evaluating the efficiency and capacity of systems, networks, processors, and applications. And there are three key aspects of throughput. Um, First is in computing, like it measures how many processes or tasks a system can handle per unit of time. And in networking, it refers to the rate of successful data transfer over a communication channel, usually measured in bits per second. In operating system, it evaluates how many jobs are completed by the system in a specific period. So the formula here for throughput is equal to total work done by total time taken. Now there are several factors affect throughput, including system hardwares such as CPU speed and RAM, network bandwidth and latency, resource allocation, and system load. For example, a network with a throughput of 100 um, um, Mbps can transfer 100 megabytes of data per second. And a CPU processing 500 instructions per second has a throughput of 500 IPS, like instructions per second. So understanding throughput helps us optimize system performance and ensure efficient resource allocation or resource utilization. Let's see our next slide. Turnaround time. Now, um, turnaround time represents the total time taken for a process to complete from the moment it is submitted until it finishes execution. This includes waiting time, time spent in the ready queue, execution time, actual processing time, and IO time if applicable. The formula for calculating turnaround time is straightforward. So you'll just say turnaround time equal to completion time minus arrival time. So a shorter turnaround time is always preferable because as it indicates a more efficient system. This metric is particularly crucial in batch processing systems where multiple tasks are queued for execution. So for example, if a process arrives at 2 p.m. and completes at 2:30, the turnaround time is 30 minutes. Now, there are several factors which influence turnaround time. First is scheduling algorithms such as first come first serve, shortest job first, and round robin. And then system load and resource availability and process priority levels. And optimizing turnaround time helps improve overall system efficiency, especially in multitasking environments where multiple processes compete for CPU time. Okay, now let's discuss an essential concept in processor scheduling, which is waiting time. Now, waiting time refers to the total duration a process spends in the ready queue, waiting for CPU allocation. It does not include the time spent executing the process or performing IO operations. So, the name waiting time means waiting. So, whatever time it takes for the process to wait for its turn to get in the processor, it is the total duration is the waiting time. The formula for calculating waiting time is turnaround time minus burst time. So where turnaround time is the total time taken from process submission to completion, and burst time is the actual time the process spends executing on the CPU. Now, some key points we have, like waiting time measures how long a process is delayed before getting CPU access, and lower waiting times improve system responsiveness and efficiency. So, for example, if a process has turnaround time 15 millisecond and burst time is 5 millisecond, then waiting time will be 15 minus 5 equal to 10 millisecond. Then several factors which influence waiting time, including CPU scheduling algorithms and process priorities which determine execution order. Then system load and resource contention, which impact how quickly processes move through the queue. So understanding waiting time helps optimize CPU scheduling and ensures fair resource allocation. Next, let's see response time, which is a critical performance metric in computing and operating systems. So response time refers to the duration between submitting a request and receiving the first response. from the system. It measures how quickly a system reacts to a user's input or process request, making it essential for real world systems, interactive applications, and web services. So, the formula for response time is time of first response minus time of request submission. So, unlike turnaround time, which considers task completion, response time focuses on the system's initial feedback. So, for example, if a user submits a search query at 2 p.m. and receives the first result at 2.2 millisecond, so the response time is 2 seconds. 2.2 seconds. So the response time is 2 seconds. So several factors same as before, like CPU scheduling algorithms affect the response time, and system load and resource availability, which determine processing efficiency, and then network latency, especially in web-based applications where quick response is crucial. So, in interactive applications such as gaming, stock trading, and web browsing, lower response times lead to better user experience. So, optimizing response time is key to enhancing system performance and user satisfaction. Okay, now let's explore how modern operating systems, particularly Windows, handle particularly Linux, handle system. Um, okay, Linux handle systems like CPU scheduling. So it uses completely fair scheduler. So it ensures fair CPU time distribution among processes, and then it uses a red black tree data structure for efficient scheduling. It assigns each process a virtual machine v runtime, and the process with the lowest v runtime gets CPU time first, and it focuses on fairness over strict priority. So every job can get a chance. So if we talk about real-time scheduling, like policies such as first come first in first out and round robin, these are the policies used for real-time scheduling. And for time critical applications where predictability is vital, it is used. um, so well, it also adjusts priorities based on process behavior. So it means you can dynamically adjust the priorities. Okay, now here we have same thing but for Windows. So Windows primarily uses a multi-level feedback queue along with quantum based scheduling and dynamic priority boosting to manage processes effectively. So multi-level feedback queue uses multiple priority levels with dynamic adjustments. High priority threads preempt lower priority ones. This is how it handles processes. Then threads that frequently yield CPU remain at high priority, enhancing responsiveness. And CPU bound processes gradually move to lower priority queues to prevent them from dominating system resources. Then quantum based scheduling, where each thread receives a specific time slice. Shorter quanta are allocated to interactive tasks, ensuring responsiveness. Then longer quanta are assigned to background tasks to allow uninterrupted execution. Now, Third is dynamic priority boosting, where it increases priority for IO bound or interactive processes to improve system responsiveness. And priority decay prevents process starvation, ensuring fairness among tasks. So, window scheduling strategies optimize performance across different workloads, whether it's real time introductions, background processing, or intensive computation. By adjusting process priorities dynamically, the system maintains a balance between responsiveness and efficiency. Okay, now let's see some of the key challenges in processor management. Um, like first one is scalability, like handling growth in workload. So as workload increases, CPUs must distribute tasks efficiently across processes. Um, then on like the key, we have a key problem, which is like load balancing across multiple processes become challenging. And then what is the solution for that? So dynamic scheduling and load balancing techniques ensure even CPU utilization and avoid bottlenecks. Then on fairness, if we talk about equals which is like which means equal CPU distribution. So every process should get a fair share of CPU time. Some processes may starve while others dominate CPU usage. And what is the solution? So priority aging and fair share models uh, prevent long-term starvation, ensuring every process gets a fair opportunity. So balancing these two aspects is crucial for optimizing system performance. While scalability ensures efficient CPU usage, fairness prevents lower priority processes from being indefinitely delayed. Alright, so now let's explore multi-core processors, a fundamental advancement in modern computing that enhances system performance and efficiency. Now, a multi-core processor is a CPU that contains two or more independent processing units. It's called cores on a single chip. Now, each core can execute instructions simultaneously, um, allowing for parallel processing and improved overall performance. So, uh, key features are like parallel processing, where multiple cores handle different tasks concurrently, leading to better efficiency and speed. And unlike single core processors that execute one task at a time, multi core systems enable multitasking and high performance computing. Second is energy efficiency. Multi-core processors deliver better performance without a proportional increase in power consumption. So instead of increasing clock speed, which generates excess heat and consumes more power, multiple cores share the workload efficiently. Next is shared cache. Now, some multi-core processors include shared cache memory to improve data access speed between cores. This allows for faster execution and optimized communication between different processing units. So, multi-core technology is essential in modern applications, from gaming and artificial intelligence to data analytics and cloud computing. It is significantly improves system responsiveness, power efficiency, and computational power. Okay, now see uh, the two primary types of multiprocessors, homogeneous and heterogeneous. So, first of all, homogeneous. Um, Here, in homogeneous multicore, all cores are identical in terms of architecture, speed, and functionality. So for example, Intel Core i7 processors, where each core performs tasks in the same way. So they are all identical. Now, these processors are commonly found in PCs, laptops, and servers for high performance computing and multitasking. Now, in heterogeneous multi-core processors, cores have different capabilities and may specialize in different tasks. So, for example, ARM processors in mobile devices using big dot little architecture, and it is found in smartphones, tablets, and embedded systems where energy efficiency is crucial. A mix of high performance and power efficient cores helps balance speed and battery life. So, um, homogeneous processors excel in uniform, high performance tasks such as gaming and software development, where heterogeneous processors optimize power consumptions, making them ideal for mobile devices and IoT applications. So, here we also have some advantages and challenges in multi-core processors. So first of all, in advantages, it improved like multiple cores allow simultaneous execution of tasks, making systems more responsive, which means it has improved multitasking performance. And then enhanced speed for parallel applications. That means workloads like video editing, gaming, AI processing, and scientific computing benefit from parallel execution. Then lower power consumption. Compared to multiple single core CPUs, multi-core processors optimize power usage, making them more efficient for laptops and mobile devices, as we saw in heterogeneous type. But there are some challenges also, like it is complex for software development, like writing programs that efficiently utilize multiple cores requires parallel programming techniques which add development complexity. Then load balancing, so ensuring tasks are evenly distributed across all cores is crucial to prevent bottlenecks and maximize performance. Then heat dissipation, so more cores generate more heat, and it requires efficient cooling solutions to prevent thermal issues. Okay, now let's discuss symmetric multiprocessing, a fundamental architecture used in modern multi-core and multi-CPU systems. Now, SMP is a processing architecture where two or more identical processors are connected to a single shared main memory and operate under a single operating system instance. Um, each processor has equal access to system resources such as memory and I/O devices. So, first of all, some key features of SMP, which has like it is symmetry, like all processors are treated equally. There is no master or slave relationship. Then so this ensures load balancing and prevents one CPU from becoming a bottleneck. Then next is shared memory. Processors communicate via shared memory, leading to faster data exchange and improved performance. It is ideal for applications requiring high speed computation and real time processing. Then, single OS control. So, a single operating system instance manages all processors, simplifying system design. And it is common in modern servers like high performance workstations and gaming PCs. Now that we have covered symmetric multiprocessing, let's shift our focus to a different multiprocessing model, asymmetric. So while say SMP treats all processors equally, AMP operates under a master-slave architecture, where one processor, the master, controls the system and other processor slaves assist by handling specific tasks. So what is asymmetric multiprocessing? So AMP is a multiprocessing architecture in which one processor, the master, is responsible for managing the system, controlling resources, and delegating tasks to other processors. Uh, these slave processors do not have equal access to system resources and only perform the tasks assigned by the master. So this model was widely used in early multiprocessor systems before the evolution of SMP and is still applied in certain specialized computing environments today. So some key features where we have like a master slave relationship, which is the main key feature. Like unlike SMP where all processors share responsibilities equally, AMP follows a hierarchical structure. The master processor handles OS level functions, including scheduling, memory management, and resource allocation. The slave processors execute specific tasks assigned by the master, such as handling IO operations or background processes. Then, task specialization. In AMP, processors are optimized for specific operations rather than general purpose computation. So, for example, in real-time embedded systems, the master processor might handle critical decision making while dedicated processors manage audio processing, network communication, or hardware control. And this is commonly seen in automotive systems, robotics, and military applications, where some processors handle safety critical operations while others manage non essential tasks. Okay, third is simplifies OS design. So it is since only one processor is the master runs the operating system, AMP requires simpler scheduling algorithm than uh, SMP. Sorry. So this makes AMP a viable choice for resource constrained systems such as embedded devices where power efficiency is prioritized over flexibility. Okay, now let's see a comparison. Uh, Now we have explored both symmetric and asymmetric multiprocessing in detail, so we'll just go through this. So as you already know, in SMP, all processors are equal, meaning any processor can handle any task, making workload distribution more efficient. And in AMP, one processor is the master and controls everything, while others are the slaves, handle only delegated tasks, leading to a hierarchical structure. Then SMP uses a single OS that all processors share, making scheduling and memory management more flexible, where AMP requires the master processor to control the OS and assign work to the other processors, reducing flexibility. Third is performance. So SMP excels in parallel processing, making it ideal for high performance computing, gaming, and cloud servers, where AMP is optimized for specialized tasks such as handling IO operations, multimedia processing, and embedded systems. Fourth is scalability. So SMP is highly scalable, as adding more processors can improve performance without major architectural changes, where AMD has limited scalability. So, like as the master processor becomes a bottleneck if too many slave processors are added. Okay, last one is fault tolerance. So, SMP is more fault tolerant as there is no single point of failure. If one processor fails, the system can continue running. using other processor. But AMP has a critical weakness, like if the master processor fails, the entire system stops functioning, and which makes it less reliable for mission critical applications. Okay, now let's focus on a critical concept that ensures efficient processor management: load balancing. So, load balancing is the process of distributing tasks, workloads, or data evenly across multiple processors, servers, or systems. The goal is to optimize performance, improve resource utilization, and enhance system reliability by preventing bottlenecks and overloading. In a multiprocessor system, some CPUs may be idle while others are overloaded. This imbalance can lead to inefficiency. So, load balancing ensures that no single processor is overburdened while others remain underutilized. Okay, some key objectives of load balancing. First of all, optimize performance. So it ensures that tasks are distributed efficiently across processors so that no single processor becomes a bottleneck, and this leads to faster execution of tasks and improved system throughput. Then enhance system reliability. It reduces the risk of system failures caused by overloading certain processors, critical in high availability systems, cloud computing, and large scale data centers. Third is improve resource utilization. So it ensures that all available processing power is used efficiently. It also prevents situations where some processors are idle while others are overloaded. Then fourth is minimize response time. It ensures that tasks are executed quickly and efficiently by dynamically balancing workloads. This is crucial in real time systems, online services, and cloud computing, where fast response times are necessary. Okay. Uh, Now, in a multiprocessing environment, multiple processes often need to access shared resources such as memory, files, or I/O devices. Without proper coordination, these processes can interfere with each other, leading to data corruption, race conditions, and system inefficiencies. This is where process synchronization comes into play. So, it is a technique used in operating systems to coordinate the execution of multiple processes. The execution of multiple processes, ensuring that the the they do not interfere with each other when accessing shared resources. Um, they execute in a way that maintains consistency, prevent conflicts, and avoid deadlocks. Imagine multiple users editing the same document at the same time. Without synchronization, changes might override each other, leading to data inconsistency. So, some key objectives of process synchronizations are like mutual exclusion. It ensures that only one process can access a critical section, a shared resource at a time, which prevents race conditions where multiple processes try to update shared data simultaneously, leading to inconsistencies. For example, if a printer queue where multiple processes request to print at the same time, mutual exclusion ensures only one process sends data to the printer at a time. Data consistency. It ensures that shared data remains accurate and consistent during concurrent access. For example, in a banking system, if multiple transactions modify an account balance simultaneously, synchronization ensures correct updates. Okay, third is deadlock avoidance. It prevents situations where two or more processes can wait indefinitely for resources locked by each other. So, for example, process A holds resource 1 and needs resource 2, while process B holds resource 2 and needs resource 1, resulting in a deadlock. So, without any of them, nobody can go to process and do the processing. So, they will be freeze forever. So, synchronization techniques prevent this scenario. Uh, Fourth one, fairness. It ensures that all processes get equal access to shared resources without indefinite waiting. For example, in CPU scheduling, fairness ensures that no process gets starved while others continuously execute. Mutual exclusion or mutex. In a concurrent system where multiple processes run simultaneously, they often need to access shared resources like memory, file, or devices. Without proper control, these processes can interfere with each other, leading to data consistency, race conditions, and system instability. To prevent such conflicts, operating systems use a key principle called mutual exclusion, commonly implemented through mutex. So, mutual exclusions ensures that only one process at a time can access a critical section or shared resource. This mechanism prevents two or more processes from modifying the same data simultaneously, thereby avoiding conflicts in concurrent execution. So, mutual exclusion is also a part of process synchronization. It is a similar thing. So it prevents concurrent access, like it ensures that no two processes access a critical resource at the same time. So for example, in a banking system, if two processes attempt to withdraw money from the same account, mutual exclusion ensures that only one transaction is processed at a time to prevent incorrect balance calculations. Then it maintains data consistency by protecting shared data from being modified simultaneously by multiple processes. Then it avoids race conditions. So these are only similar to the process synchronization. What process synchronization does, it is mutual exclusion is a function like that. So it ensures that operations occur in the correct sequence when multiple processes interact with shared resource. Like if you try to book an online ticket and there is only one ticket left, so if two people are trying to purchase one ticket, and uh, then only one will get it because there's only one seat available. So it prevents double booking of one seat. So these are the section where mutual exclusion works. Okay, some techniques for achieving mutual exclusion. In order to maintain data consistency and prevent race conditions, operating systems implement various mutual exclusion techniques to regulate access to shared resources. These techniques ensure that only one process accesses a critical section at a time. First of all, locks. Locks are basic mechanisms that restrict access to shared resources. So, we have two types of lock: simple lock and spin lock. On simple lock, a flag that indicates whether a resource is in use or available. When a process acquires the lock, others must wait until it is released. Simple but can lead to busy waiting, like wasting CPU cycles. Where spin lock is a type of lock where a process continuously checks if the lock is available, and if it is efficient for short waits, but can be CPU intensive if the lock remains unavailable for long. And it is commonly used in multi-core systems where context switching is expensive. Second is semaphores. So a semaphore is a synchronization tool that controls access to shared resources. um, we have binary semaphore 0 or 1, like work like it also works like a lock. So a process can either lock 0 or unlock 1 a resource, which ensures that only one process accesses a resource at a time. Then counting semaphore, um, which allows multiple processes to access a resource simultaneously up to a defined limit. For example, like database connections where multiple users can read data but only a limited number of can modify it at once. Okay, third is mutex, mutual exclusion lock. So a mutex is a specialized lock that ensures only one process or thread can access a resource at a time. Unlike a simple lock, a mutex includes mechanisms to prevent deadlock and priority inversion. For example, a printer queue where multiple users submit print jobs but only one job is processed at a time. Okay, fourth one is Peterson's algorithm. It is a software based solution to enforce mutual exclusion between two processes without relying on hardware locks. It uses flags and turn based conditions to control access. It is mostly used in theoretical computer science but important for understanding process synchronization. Okay. In a multiprocessing environment, multiple processes often compete for shared resources. However, if a set of processes wait indefinitely because of each is holding a resource while waiting for another, a deadlock can occur. This results in a system halt where no process can proceed. So, what is a deadlock? As I said, a deadlock occurs when a set of processes are permanently blocked because each is waiting for a resource held by another process. This creates a cycle of dependencies, preventing further execution. And like imagine a traffic intersection where four cars are blocking each other in a circular pattern. No car can move because each is waiting for another to move first. Similarly, deadlocks in computing cause processes to remain stuck indefinitely. Conditions for deadlock. For a deadlock to occur, all the following four conditions must be held simultaneously. First of all, mutual exclusion. At least one resource must be held in a non-shareable mode. Only one process can use it at a time. For example, a printer can only process one print job at a time. Hold and wait. A process is holding at least one resource and is waiting to acquire additional resource held by other process. No preemption. Resources cannot be forcibly taken from a process. They must be released voluntarily. For example, a process that has acquired a file lock must finish its operation before releasing it. Okay, fourth one is circular wait. A circular chain of processes exists where each process holds a resource needed by the next process in the chain. For example, like a process A holds resource X, waiting for resource Y, which is held by process B, and process B holds resource Y, waiting for resource X, which is held by A. And now in all four conditions, if all four conditions are met, a deadlock occurs and the system halts. So what are the prevention techniques for deadlock? So deadlock prevention focuses on ensuring that at least one of the Kaufman's conditions, like mutual exclusion, hold and wait, no preemption, circular wait, any of these four conditions like does not hold, thereby avoiding deadlocks entirely. So first of all, we'll try to eliminate mutual exclusion. We'll try to make resources shareable where possible. Like for example, read-only files can be accessed by multiple processes simultaneously without conflicts. And this method is effective for resources that do not require exclusive access, but some critical resources must remain non-shareable, limiting its effectiveness. Second, we'll try to eliminate hold and wait, which require processes to request all required resources at once before execution begins. So, which prevents processes from holding resources while waiting for others, which reduces the risk of deadlocks. But it can lead to resource underutilization. Processes may hold resources they don't use immediately, and which can cause starvation, where low priority processes wait indefinitely. Third is we can try to eliminate no preemption. So, allow preemption of resources, meaning that resources can be forcibly reclaimed from processes when needed. This approach ensures that essential resources remain available for critical processes but can lead to process interruption and inefficiencies. So, for example, in CPU scheduling, a high priority process can preempt a lower priority process's CPU time, ensuring efficient execution. Then lastly, we can try to eliminate circular wait. So by imposing a strict ordering of resource request to prevent circular chains from forming, and we will assign a numerical value to each resource, like for printer it's 1, disks 2, memory 3. So processes must request resources in ascending order, like never in a cycle. So for example, if a process requests a printer 1, it cannot later request memory 3 before releasing the printer. This method effectively breaks the circular wait condition but restricts the flexibility of process execution. Okay, now how can we detect the deadlock? Like we saw what is deadlock, what is the occurrence, how it happens, and how can we avoid it, but how can we detect it? Deadlock detection is particularly important in dynamic systems such as operating system, databases, and cloud computing, where resource allocation changes frequently. So here we have some methods. So first of all, we have resource allocation graph method. It is a graph-based representation that shows processes and resource dependencies. Nodes represents processes and resources, while ages indicates um, resource requests and allocations. So a deadlock is present if the graph contains a circular weight. So if you have a representation, graph based representation of your process, and if it looks like if it contains a cycle, then you can find there is a deadlock. Second, Banker's algorithm for deadlock avoidance and detection. So it is used to avoid deadlocks by simulating resource allocation request. Before granting a request, the system checks if allocating the resource will lead to a safe state. If no safe sequence is found, the request is denied, preventing a deadlock. So it is used in banking systems to ensure accounts always have a safe state when processing multiple transactions. Third is wait for graph, like a simplified version of a RAG, where only process dependencies are tracked, which ignores resources. So if a cycle is detected, a deadlock exists. Fourth is detection algorithm for multiple resource instances. Uh, More complex detection method used when multiple instances of a resource are available, and it uses matrix based tracking to identify if a system has reached a deadlocked state. Uh, for example, it is used in databases, while enterprise level cloud computing environments where like multiple servers allocate shared resources. Fifth is periodic deadlock checks. So, some operating systems perform scheduled deadlock detection at intervals. So, this prevents long term systems halts and allows for deadlock resolution strategies such as terminating or rolling back processes. Okay, so first of all, we learn the occurrence, then the how we can avoid the deadlock. Then we saw the deadlock, how we can detect the deadlock. Now, after all of this, if deadlock happens, how can we recover that? So this is also like similar techniques. These are also similar things that we have learned so far. Like first of all, process termination. We have to terminate one or more processes involved in the deadlock to break the cycle. So then resource preemption, like we have to forcibly reclaim resources from one or more processes and allocate them to others to resolve the deadlock. Then third, process rollback. We can roll back one or more processes to a previously known safe state and restart them to avoid deadlock. Then killing processes, like last resort. This is the last resort. If other methods fail, terminate the process causing the deadlock most frequently, or the one with the least priority. Okay, now in real-time computing, tasks often have strict deadlines, meaning some processes must be prioritized over others. Um, to ensure time execution, one of the most widely used real-time scheduling algorithms for this purpose is earliest deadline first scheduling. So EDF is a dynamic priority scheduling algorithm where the task with the closest deadline is given the highest priority. It is used in real-time operating systems where task deadlines must be met to avoid system failures. So, unlike fixed priority scheduling, where tasks have been predefined priorities, EDF dynamically adjusts priorities based on deadlines. This ensures that urgent tasks are executed first, which improves sensitive processing. like time sensitive processing. So second is it supports both primitive and non-primitive scheduling. Like a newly arrived task with a closer deadline can interrupt on ongoing task. And on non-preemptive mode, once a task starts execution, it cannot be interrupted until completion. Okay. Third is it ensures optimal CPU utilization if the system is not overloaded. So EDF scheduling achieves 100% CPU utilization in ideal conditions, meaning all deadlines can be met if system load is manageable. However, if the system is overloaded, some tasks may miss their deadlines, leading to performance degradation. Okay, now in real-time systems, tasks often need to be scheduled based on how frequently they occur rather than their deadline. This is where rate monotonic scheduling comes in, a widely used fixed priority scheduling algorithm for periodic tasks. Uh, Unlike earliest deadline first, where which is the dynamically assigned priorities, RMS follows a static priority assignment based on task periodicity. Um, RMS is a fixed priority real time scheduling algorithm that assigns high priority to tasks with shorter periods. It is optimal among fixed priority algorithms for scheduling periodic tasks on a single processor. Um, Tasks with shorter execution cycles, like high frequency, receive higher priority. Tasks that execute less frequently have lower priority. For example, if a task that runs every 10 milliseconds has a higher priority than a task that runs every 50 milliseconds. So, um, RMS guarantees schedulability if the total CPU utilization you satisfied, um, then RMS assumes no dependencies between tasks. If a higher priority task arrives while a lower priority task is executed, preemption occurs, meaning the lower priority task is paused. Fair scheduling. In most computing environments, fairness is a key factor in scheduling processes. So, unlike real time scheduling algorithms like RMS or EDF, which prioritize time sensitive tasks, fair scheduling ensures that all processes get a reasonable share of CPU time based on a specific rules. Fair scheduling is particularly useful in multi-user systems, cloud computing, and network traffic management, where multiple processors or users need equal opportunities to execute. So we'll see some um, popular um, fair scheduler here. Um, so here we have Completely Fair Scheduler (CFS), which is used in modern Linux kernels as the default scheduling policy. It distributes CPU time based on virtual runtime, ensuring that each process gets a fair share. How it works. So processes with less CPU time are prioritized to balance execution fairness. Unlike traditional round robin or priority scheduling, CFS does not use fixed time slices but continuously adjusts execution time to ensure fairness. For example, um, It is used in desktop operating systems, servers, and cloud computing environments to allocate CPU fairly among multiple tasks. Weighted fair queuing. It assigns weights to processes where higher weight processes receive more CPU time. Balances fairness while allowing priority differentiation, important in networking and QoS, which is quality of service management. It is used in network routers like higher priority network packets to get more bandwidth, while lower priority packets get less. Um, okay, third is lottery scheduling. It is like a lottery, like randomized scheduling algorithm, where processes receive tickets representing chances to win CPU time. So the more tickets a process has, the higher its likelihood of getting scheduled, ensuring both randomness and fairness. Okay, processor affinity. So, what is affinity? Well, in modern multiprocessor systems, processes can be scheduled to run on any available CPU core. However, frequent switching between cores can lead to cache inefficiencies, which cause performance degradation. Processor affinity, also known as CPU pinning, helps optimize performance by binding a process to a specific CPU core. So, processor affinity is the practice of assigning a process to a specific processor or core to minimize cache misses, improve performance and efficiency, reduce CPU switching overhead. Um, so basically, it enhances performance by ensuring that a process consistently runs on the same processor instead of frequently switching between different cores. Then it reduces memory latency by utilizing processor cache locality. When a process stays on the same CPU, it can reuse cache data, reducing the need to fetch data from RAM. Now there are two types of affinity, soft and hard. So first is advisory. The operating system attempts to keep a process on the same CPU but does not enforce it strictly. If necessary, the OS can still migrate the process to another CPU for load balancing. And on hard affinity, it is strict, like it has to be, it just forcefully take attempts to keep a process on the same CPU. Okay, hyperthreading and its impact. So, when handling multitasking and high performance applications, one technology that significantly enhances CPU performance is hyperthreading, developed by Intel. Hyperthreading allows a single physical processor core to behave like two logical processors, improving the overall efficiency of instructions execution. Now, what is hyperthreading? It is a hardware technology that enables a single physical CPU core to execute multiple instructions threads simultaneously. Each core is divided into two logical processors. Each core divided into two logical processors, allowing the CPU to handle more tasks in parallel without requiring additional physical cores. It is introduced by Intel to improve parallelism and CPU resource utilization. Now, a single core has two separate execution units that can process different instructions threads concurrently. While both logical processors share cache, execution units, and memory bandwidth, they efficiently schedule instructions to reduce CPU idle time. And this means that if one thread stalls due to a data dependency, the second thread can continue execution, which improve overall CPU throughput. So it enables better multitasking by allowing multiple threads to execute simultaneously. It improves performance in applications optimized for parallel execution, and it reduces CPU idle time. Then for resource sharing, logical processors share CPU resources, meaning that while execution improves, performance gains depend on workload type and CPU design. Power efficiency. It allows more work to be done per clock cycle without increasing power consumption significantly. So, fourth one is workload impact. So best suited for multi-threaded applications such as gaming and streaming, data processing and AI workloads, web servers and cloud computing, but it's not useful for single-threaded applications as the performance gain relies on parallel task execution. Virtualization and processor management. Now we already saw virtualization in our part 1, I think so. We'll now see like virtual machines or containers. How virtualization allows multiple virtual machines or containers to run on a single physical processor. It effectively divides computing power between multiple users or applications, which improves resource utilization, cost reduction, and flexibility. So, first of all, CPU resource allocation. What is the impact on processor management? So, Hyper-V like VMR, KVM, or Hyper-V, these manage CPU cycles between different virtual machines. The system dynamically assigns CPU time to ensure optimal performance across workloads. Processor overhead. So virtualization introduces some processing overhead as the hypervisor must manage multiple VMs. Advanced technologies like hardware assisted virtualization, like Intel VTX, AMD V, these help minimize this overhead. Okay, load balancing and scheduling. Uh, Virtualized environments dynamically distribute processing loads across available CPU cores. Isolation and security. Virtualization ensures process isolation, meaning one virtual machine's failure does not affect others. Scalability and flexibility. Businesses can scale CPU resources up or down depending on demand. Cloud platforms like AWS, Azure, and Google Cloud uses virtualization to provide on-demand computing power. Okay, containerization and process scheduling. What is containerization? Um, Containers play a significant role in modern cloud computing, microservices architecture, and DevOps workflows. Um, Container provide a lightweight, efficient way to package and run application in isolated environments. So basically, containerized applications are self-contained software packages that include all necessary code, libraries, and dependencies to run consistently across different computing environments. So unlike VMs, containers share the same OS kernel but remain isolated from each other, reducing resource overhead. So some popular containerization tools are Docker. It is most widely used container platform. Kubernetes or orchestrates and manages containerized applications. Podman, a rootless, daemonless container engine. Now, what are the challenges in multiprocessor environment? Um, First of all, resource contention. Containers compete for CPU resources, which can create performance bottlenecks if not properly managed. And this is particularly critical in high density cloud environments where multiple containers run on shared CPU cores. Second is scheduling complexity. Balancing workloads across multiple processors is challenging when dealing with dynamic container scaling. The OS and container orchestrators must allocate CPU cycles efficiently to prevent idle CPU time. CPU affinity issues. Um, like traditional processes, containers can benefit from processor affinity to optimize cache performance. If a container is frequently moved between CPUs, it may lose cache data, causing unnecessary delays. Okay, now we already know about load sharing and load balancing. You will have an idea if you read this table with those aspects. So I'm just skipping it. I'm not reading all this table, whatever is here, because we already have that in our previous slides. So we have an idea what is load sharing, what is load balancing. So you will see, you will read that table, and I hope you will understand what is the difference between them. So now we'll see energy efficiency in processor scheduling. So efficient processor scheduling helps manage power consumption dynamically, ensuring optimal performance while reducing energy waste. So um, it is not just about reducing power consumption, it plays a crucial role in minimizing operational cost, extending battery life, and lowering the environmental impact of data centers. So, um, first of all, if we talk about key techniques for energy efficient scheduling, first of all, we'll have dynamic voltage and frequency scaling, which adjusts CPU voltage and frequency dynamically based on workload, which lower frequency reduces power consumption while higher frequency provides performance when needed. Second is dynamic power management. It automatically powers down unused components to save energy. Third is energy aware scheduling algorithm. It modify task scheduling based on power consumption metrics rather than just CPU availability. Then processor affinity for cache efficiency. Like assigning processes to specific CPU cores to reduce cache misses and memory access latency. Task consolidation, which reduces the number of active processors by scheduling tasks on fewer cores while keeping others in low power mode. Then thermal aware scheduling. Um, it prevents CPU overheating by distributing workloads evenly to avoid hot spots. Then lastly, sleep modes and idle states. So modern processors enter low power sleep states when idle, which helps laptops and mobile devices conserve battery by reducing background power usage. Okay, quantum computing and processor management. So traditional computing relies on classical processors that use binary bits like zeros and ones, like to perform computation. However, quantum computing is revolutionizing the way we process information by leveraging the principles of quantum mechanics, such as superposition and entanglement. So, um, quantum computers use qubits instead of classical bits, allowing them to perform multiple computations simultaneously, enabling massive parallelism that classical systems cannot achieve. So basically, um, the key difference is like on classical processor it uses 0 or 1, and quantum processing use qubits sequentially, it uses qubits, um, which can be 0 or 1 or both at the same time. Then qubits can be entangled, meaning the state of one qubit is directly related to another, improving computational efficiency. So, how quantum processors are managed? First of all, qubit allocation and scheduling. Like unlike classical CPU scheduling, quantum scheduling optimizes qubit usage to maximize computational efficiency. Qubits must be carefully assigned to prevent decoherence, a phenomenon where quantum states collapse due to environmental interference. Error correction and noise management. Quantum computing is highly sensitive to noise, requiring quantum error correction to maintain accuracy. Hybrid quantum classical scheduling. Um, since quantum computers are not yet fully self-sufficient, many applications use a hybrid model where classical processors handle some tasks while quantum processors perform complex calculations. Then, lastly, resource optimization. Quantum systems require extreme cooling near absolute zero to function efficiently. So, quantum computing is our future. So, we don't have a fully uh, uh, quantum computer. Like, we have a hybrid model where some features are used in classical computing and some are quantum, but not fully in quantum computing. So but we are towards that area, that time that will have, hopefully will have quantum computing very soon. Okay, security considerations in processor management. Now, after all of these, we have to maintain the security, and there are so many security threats in CPU scheduling, like data leakage, privilege escalation, denial of service attacks, side channel attacks. We'll learn about those things. So we'll have another topic on security. So uh, we'll just you can just have that for your information, that these are the key techniques for securing CPU scheduling, but we'll have a detailed topic and lecture later for security. So that's all for today's lecture. You'll find your homework 1 in Moodle, so please make sure you start your homework early so that you can finish it by before due date, because I will not accept any late homework or homework through email. You have to submit your homework on Moodle before the due date. And if you have any questions regarding homework or if you need any help, please let me know. You can email me anytime. So we'll have our next lecture. I will post the next lecture soon. Thank you.